Here's a view of the finished product, an end table on casters with a telescoping extendable surface. I was asked to design and build this end table to fit in a small space between a couch and the wall for a city apartment. First I sketched out what could go there. The 9.5-inch wide tabletop was to fall below the windowsill and below the rolled edge of the couch, either 13 or 16 inches high. The bottom of the space has a radiator on the wall which limits the base to 8 inches wide, and a ball valve handle sticks out of the radiator another 3 inches. In addition, an electrical outlet needs to be accessible below the table's surface. There was some discussion about the optimum height for the table, being 13 or 16 inches, so I offered a button-actuated telescoping leg arrangement that would let the height be adjustable in half-inch increments. An additional feature requested was to have a telescoping extendable shelf from the front to place items like books, papers, or a laptop, or smartphone while charging, or working from the couch. We decided on a trestle-style wooden tabletop over a steel frame on casters to offer easy access to the electrical and plumbing utilities below. The wooden top would be made from a sandwich of 3 boards, allowing the middle layer of the sandwich to telescope out from the front. The steel frame would support the load from a trestle design. I drew the table plans in Keynote, the presentation app on the Mac, keeping all the parts to scale. The sliding layer of the sandwich design, shown in green, could be cut down on the sides and fit in between the side rails, shown in violet. The side rails could be cut from the sides of the center layer and glued in place to hold the top and bottom layers apart. The sliding middle layer would need to be thinner than the side rails to slide smoothly after the finish is applied. The legs would be made from 12-gauge steel square tube and 3-inch wide steel plates 3/16 of an inch thick. The square tube would allow the legs to telescope to fit different heights. I would need to make some buttons from stainless steel to lock the legs at the desired heights. The non-sliding parts could be welded together for high strength and stability. Casters on the bottom will prevent scratching a wood floor and provide easy access to any plumbing and electrical utilities below. We selected a beautiful 9.5-inch wide, 9-foot piece of maple that was plain smooth on all 4 sides, having only one knot that would go on the bottom. Using the radial arm saw, I cut the board squarely into 3 sections for the tabletop. I ripped the side rails from the board which would become the center layer. I finished the square cuts at the end with a handsaw. Here is how the maple parts will fit together. The middle layer telescopes out from the bottom layer, and a stop block will be screwed to the back end of the middle layer to keep it from overextending. The side rails will be glued on the sides of the center layer to limit the travel of the stop block in the middle layer. The top layer is glued to the tops of the side rails, allowing the middle layer to slide freely, telescoping out from the front. I actually played this shot backwards because it was tedious to fit together on camera. Next, we use a planer to make the middle layer thinner than the side rails. A finish sander takes out any ridges left from the planing process. A chisel is handy to carefully trim off the excess wood left by the thin kerf of the handsaw, being careful not to chop off the front section of the slide-out telescoping middle layer. Now we can glue the side rails to the bottom layer. I learned that if you put a few grains of salt into the glue, the grit of the salt helps keep the parts from sliding around while you set the clamps in place. The small amount of salt does not affect the glue adhesion and actually dissolves as the glue sets. You could use a few grains of sand, but sand won't dissolve and it might damage your planer if you plan to use one to clean off the excess glue. Calling all clamps. It started getting heavy on one side, so I added some toolboxes for counterweights. After gluing the other side rail the same way, I applied a coat of polyurethane to the inner surface to limit moisture intake and warpage, which might cause binding of the middle layer. I covered the glue joint surfaces with masking tape to keep the finish off them for subsequent glue up. I tried the middle telescoping shelf layer one more time before gluing up the top layer to make sure it was still sliding freely. Next, I applied some glue to the bare wood surfaces where the top layer is attached. I had previously dry fit the top and used masking tape strips to mark the approximate positions where the clamps would fit based on the number of clamps I had available. I placed softwood pieces between the clamps and the maple surface to prevent marking the surface. I had to elevate the workpiece off the benchtop on blocks to fit my hodgepodge of clamps underneath the edges. Once the glue has dried and the big drips have been removed with a wide chisel, the planer smooths the 3 layers to become one smooth surface. A quick pass over the edge face removes any burn marks from the saw blade and levels out any inconsistencies. The belt sander makes short work of the final smoothing, and the square shows the edge is perfect. The finish sander prepares the surface for the finish coating and rounds off any sharp edges left by the planer. The steel for the legs was ordered cut to size. Here's a quick animation showing roughly how the parts will be welded together. Before welding, we need to drill some holes into the plates that will be screwed into the bottom of the wood top. Drilling 2 at a time requires less setup and ensures the holes will be in the same place on both parts. A little oil helps the cutting process and keeps the drill from overheating. Next, we need to drill the adjustment position holes into the telescoping legs. First, we drill a pilot hole, then countersink down to make a recess to fit your finger. I like the cross-slide vise from Harbor Freight. It makes it easy to drill and countersink a series of holes. After the holes are drilled, we need to run a file inside to remove the burrs and the weld seam from inside the square tube. A trial fit of the smaller tubes shows they fit and slide in and out freely. Now it's time to start welding the steel legs together. The rule of thumb is 1 amp per thousandth of an inch, so since the steel is 125 thousandths thick, we'll start at 125 amps DC minus polarity for deep penetration. We can adjust up or down from there as needed. Make sure you wear your old clothes when welding, as the hot sparks destroy everything they touch. Welding magnets are used to hold the parts square for initial tack welding. Each side is tack welded, then checked for square before the full weld bead is laid down. I like 70-14 rods for all-around welding. The 70 means the weld has a tensile strength of 70,000 pounds per square inch, and the 14 describes the weld position, the AC/DC use, and the flux coating on the welding rod. They leave little slag and form a smooth bead for me. They're easy to find charts on the internet that show you what the codes mean if you want more. First, I'm welding the larger 1 1/4 inch square tubes to the smaller top plates that have 4 holes drilled to mount on the underside of the tabletop. These plates are only 6 inches wide, and the square tubes are 1 1/4 inches on the outside. These larger square tubes with the multi-position holes will slide down over the smaller 1-inch tubes. Next, I'm welding the smaller 1-inch square tubes to the bottom plates that will have casters on the bottom. These 1-inch tubes will fit inside the larger 1 1/4 inch tubes. The bottom plates are 8 inches wide to give the table a stable stance. And even with the casters, it still fits under the edge of the radiator. Just to be sure, I tape the casters to one blank bottom plate before welding and confirm that it will fit under the radiator to make sure all measurements and calculations were correct. After each weld, it's necessary to chip off the slag that forms over the actual weld and clean it with a wire brush to visually inspect the weld for voids. Any voids can then be touched up. After welding, a grinder is used to smooth down the weld metal. In some cases, I used a round file to create a smooth fillet. Next, I used a rotary grinder to finish the welds so that they blend in and appear seamless. Starting with the smallest grinding wheel, I worked up to larger sizes until the welds were almost invisible. Quarter-inch stainless steel bolt is my choice to make the locking buttons for the telescoping leg height adjustment. First, we grind the head off the bolt on the bench grinder. The bolt started to get hot, so I had to use vice grips to hold it. Once the head is all ground off, we move to the drill press and turn the bolt while we grind a bullet shape for the button. Next, we turn the bolt around and put it back in the drill press to cut the threads off. I leave some space of the threads because we can grind that down to a bullet shape for the second button. Once we've cut 3/4 of the way through the bolt, we can simply stop the drill press and break it off with a pair of pliers. Repeating this process on the other end of the shank, we're left with a shape that looks like a bullet. Here you can see we're putting the bullet back into the drill press now, upside down, so we can drill a small hole into it and then tap threads into the hole to accept the screw. First we use a center bit to drill a hole in the bottom of the button. Next we use a twist drill to drill the rest of the hole. It's easier to drill a hole by spinning the piece and holding the drill bit stationary, as we're doing here, because the drill naturally attempts to center itself on the slowest section of the rotating button, finding the center better than we can on our own. Once we've drilled the tap hole, we can tap threads into the button. As you can see, we're starting the threads here. This is the most difficult part in fabricating the buttons, because the taps kept breaking inside the buttons. In fact, I broke 3 taps while making these 2 buttons. 2 5.5-inch lengths of stainless steel band, normally used to hold home TV antennas to chimneys. The steel bands will be bent to form spring clips to hold the buttons inside each leg. Next, we drill a small hole in the end of the stainless steel band to accept the button. Then we use a screw to attach the button to the steel band through the holes we drilled and tapped. Now we bend the band into the shape we need to fit inside the tube. Next, we put the newly made spring clip with the button inside the smaller 1-inch square tube. Now we slide the 1-inch tube inside the 1.25-inch tube to test the fit. Both legs worked fine. Now we can weld the crossbeam in place that holds the 2 legs together. The crossbeam is a 12-gauge 3/4-inch steel tube. The crossbeam will tie the 2 legs together for stability under the table. A quick check with the square confirms that the welding magnets are holding the crossbeam in the correct position for welding. In the welding process, the electrode is walked back and forth across the gap to make sure the heat and molten steel flow evenly across the joint. Once the crossbeam is welded in place, it's time to attach the casters. I wrap the bearings with masking tape to keep the sputtering sparks of steel balls from getting into the ball bearings during welding. A metal shield will be placed over the wheel to keep the sputtering sparks from landing on the rubber wheels of the casters. Then we clamp the telescoping leg base to the bench and position the caster for welding. I found that the casters had a high spot in the middle, so I placed a small shim under the caster while clamping to weld the first side. Then I place a heat shield over the caster and weld a small bead along one side of the caster. A cooling spritz of water prevents excessive heat from melting the plastic ball retainer of the caster bearings. Then we can take off the caster clamp and the shim. Next we replace the heat shield and draw a bead on the other side of the caster, followed by a spritz of water. Then we can turn the leg base around and weld on the other caster. I chose to weld the casters in place because it was cleaner looking from the top surface to have no visible fasteners, and I was confident that they would fit under the radiator. Onto the bench grinder to scrub the welds with the wire wheel. Once all the steel work is done, a coat of gray primer coats all the steel parts. Next, all the steel is coated with glossy black. Unfortunately, the thickness of the coating became a problem for the telescoping legs, making them bind up. So I had to clean the 1-inch square tubes down to bare metal and spray the black coating on them. Then the coating was thin enough to let the legs telescope freely again, as you can see here. A coating of automotive wax and some silicone spray inside the telescoping sections helps to keep the parts moving freely for the long term. You can also see the casters move freely too, which I painted black, except for the blue wheels. Now it's time to mount the leg assembly on the bottom of the wood top. The screws go through holes that were drilled in the steel plates before welding. Now we flip the whole table over so we can insert the telescoping middle layer. Well, it still fits with all the layers of polyurethane coating. I sprayed the polyurethane on the wood, wet sanding in between coats after each overnight drying. Now it's time to put the handle on the telescoping middle layer. I put some masking tape on first to protect the edge from any errors or erroneous markings. The handle fits well with about 2.5 inches of space on each side. First, we mark the approximate locations for the screw holes with a pencil. Once we have marked the exact locations for the screws, an ice pick is used to pinpoint the hole locations. Then a pilot hole is drilled for each screw, and the handle is fastened in place. A quick test shows it still works. Now we can spin it around and knock over the cordless drill. Next, we install the stop block, which keeps the telescoping shelf from extending beyond 20 inches. Lastly, we install the turn button we made on the back. This will keep the telescoping shelf from extending during moving. Here's a close-up of the brass parts after being sprayed with polyurethane. Since brass tarnishes with time, the polyurethane coating should keep the brass bright for a good long while. The brass handle came from an old blue porcelain teapot. It was held on with a rivet and a washer-type retaining clip. I reshaped it with a plastic-faced hammer over a section of 3-inch steel pipe and used some flat-nosed pliers to reshape the bend on one end to match the other end. Next, I polished it up with some Knox-On metal polish to revive it and remove any tool marks. Then I used a countersink off camera to fit the brass flat head screws. I fabricated a turn button from an old brass faucet stem and polished up all the brass parts, including the screw heads, to prepare them for the polyurethane coating. Thanks to Fewer Lumber in Atkinson, New Hampshire for that beautiful 9-foot piece of maple. They are a great family lumber yard with a friendly atmosphere, personal service, top quality materials, and highly competitive prices. Thanks to Magna Steel in Beacon Falls, Connecticut for having a great inventory of steel to choose from and personal service. They provided accurately clean sawn steel to specified lengths ready for welding. Thanks to Last & Last brand of polyurethane for providing a beautiful, durable gloss finish. And Rust-Oleum Gloss Black for providing a durable black glossy finish. All finished spray coatings of polyurethane and Rust-Oleum were thinned with naphtha, which evaporates faster than paint thinner. All parts were sprayed with a $10 airbrush kit from Harbor Freight. I hope you enjoyed watching this project come together. I know Small Pink Bear enjoyed it.